Imagine a world where problems that used to take billions of years can be solved in mere seconds. Welcome to the era of quantum computing. Good morning. My name is David Rodriguez.
My name is Mark Kolzar.
My name is Ruben Heyer.
And my name is Tyler Nichols. Our research answers the question, to what extent are advancements in quantum computing impacting various industries, including the potential ethical implications associated with its widespread adoption?
Our answer is quantum computing has provided a valuable framework for network security, facilitating effective developments in medical research and government regulations, while still being bounded by trade and end use controls.
To begin with, what is quantum computing? Quantum computing takes advantage of quantum mechanics and associated principles to perform complex calculations. Some of those principles include quantum superposition and the operation of qubits. According to Donna Liu, a writer for The Guardian in Australia, she writes that quantum computers can perform calculations at rates unparalleled with those of classical computers. Lowell K. Grover, a renowned Indian-American computer scientist, best known for the creation of the Grover search algorithm, expounds how an electron can store bits of data, as every electron acts as if it were a little magnet, spinning about an axis whose magnetic moment can point only one of two directions, up or down. Thus, the spin state of an electron can be leveraged to store a single bit of data, and with millions of subatomic particles present, colossal quantities of data could be stored, as shown by this infographic, with the upstate being correlated to 1 and the downstate being correlated to 0. In addition, David Ostrom, a vice dean for research at the Christopher School for Molecular Engineering at the University of Chicago with a PhD in experimental physics from Cornell University, highlights how a nitrogen vacancy center within the crystalline structure of a diamond molecule could be used to emit light radiation after electrons within this nitrogen vacancy center absorb infrared radiation via a laser, in which the fluorescence intensity of such emitted light radiation could be for spin state readout, with bright for state 1 and dim for state 0, as we can see in this image, in which electrons within the nitrogen vacancy center absorb infrared radiation via this laser, and as a result, they're able to emit light in the form of photons, thus preventing a cyclic movement of data.
Quantum physics has been revealed as the next stage in the information revolution due to implication in computational strength and efficiency. According to Zhua Jin at the Harbin Institute of Technology, China conducted a successful data transmission via quantum satellite in early 2020. The message was hyper-encrypted and traveled the distance shown in this visual, from base to medium, approximately 1,120 kilometers. The promise nearly entirely lies in the cryptographic scheme known as quantum key distribution. The University of Sydney Department of Physics concluded that if entangled photon arrivals are recorded as ones and non-arrivals as zeros, then a truly random binary string will be generated. The first step is for Alice, the sender, to create this random sequence. The qubits are encoded at the subatomic level, then sent to Bob, the receiver, via optical channel. Bob decrypts and records their quantum states, notifying which qubits could be deciphered. The resulting key is exclusive to this communication channel and future-proof. Ergo, its security is not compromised by future advancements in technology. In the event that an eavesdropper Eve attempts to intercept this communication channel, she will inevitably disrupt the qubit states of uncertainty that Ruben previously mentioned. The current optimal traditional cryptographic scheme in asymmetric transmissions is elliptic curve cryptography. When comparing its performance to quantum testing, it's clear that classical algorithms, even at their maximal input, can be easily broken through the rapid simultaneous searches done by quantum devices. Discrete and logarithmic mathematical problems, such as complex prime factorization that interference defense currently relies on, might be rendered obsolete in the coming years for this very reason. Google's qubit processor Sycamore represents quantum supremacy in performing a task that would take the world's largest and most powerful supercomputer 10,000 years in little over 3 minutes.
The application of encryption plays a key role in the positive ethical uses of quantum computing's involvement in cryptography. Thomas Philbeck and Nicholas Davis, the authors of the academic peer-reviewed journal, The Fourth Industrial Revolution, Shaping a New Era, credited quantum computing's advanced operation systems for its encryption of classified data. As people communicate online, data is sent and received through encrypted code that the receiver can recognize and decipher. As David previously mentioned, this encryption of sent information along with the storage of data is strengthened through stronger and more complex equations of encryption that classical computers cannot offer. This being said, quantum computing's role in decryption proves ethically fallacious. Steve Grobman, Senior Vice President and Chief Technology Officer of McAfee, writes on quantum computing's abilities to decrypt encrypted information that would take classical computers many years to compute in a matter of minutes. This brings about the worry of bad actors who, with access to quantum computers, could decrypt encrypted information that would leak personalized data of citizens and governments. As seen in this chart, the y-axis represents the length of time data needs to be kept secret, and the x-axis the sensitive data. This shows to an extent the types of information which is kept private by encryption, protecting not only classified government information, but also the data of citizens. According to this graph, there are different ways quantum computing's advancements in encryption are benefiting society, but also the detrimental impacts quantum computing's decryption abilities can have on a variety of encrypted data.
Anand Quayam, an associate professor of education innovation at Athabasca University, explains how quantum computing can develop supersonic drugs because of its ability to do quick DNA sequencing. This opens up the possibility of pharmaceutical companies to save billions of dollars, open up being able to put new drugs onto the market. Elaborated by the 7 Sense Research Group, stating how unlike classical computers, quantum computers aren't limited to size and designs of the drugs, allowing pharmaceutical companies to save billions of dollars during the time it takes to introduce new drugs on the market. According to the Moffitt Cancer Center, adaptive radiotherapy is a type of radiation therapy that involves continual adjusting treatment to account for changes taking place within the patient's body, administering the most accurate radiation dosage possible, sparing all the surrounding tissue. From the Missouri State Medical Association, Mrs. Jones was cancer-free but has recently been identified with a 1/10 millimeter square cluster of cancer cells near the original surgery site. Through adaptive radiotherapy, the radiation beam destroyed the cancerous cell with an extreme precision, sparing all the surrounding tissue. Healthcare data is transmitted over an open channel, allowing hackers to breach and alter sensitive data, allowing third-party interaction with your medical data, which blockchain technology can help solve. In this figure, it shows a patient and a doctor which primary data is generated. This creates an EHR in step 2. In step 3, customized user access is created where only the owner can give access to others. In steps 4 to 6, database and cloud storage store and record the data, while blockchain technology secure the privacy of that data. In step 7, healthcare providers must request access from the owner for that information. For quantum computing to be integrated successfully, it should follow the following prospects of global collaboration, allowing transparency, which prevents misuse by making publicly findings of quantum computing. A supervisory body would be administered to ensure that standards aren't violated by organizations. And quantum-resistant encryption prevents sensitive data from being breached.
While these solutions to quantum computing may seem feasible, there are limitations associated with them. For instance, quantum key distribution is subject to denial of service attacks. For instance, point-to-point key exchange. Additionally, quantum devices operate optimally near sub-zero level temperatures. Thus, any deviations away from such temperatures could seize the functioning of certain quantum computing systems.
Ultimately, we decided that the most reliable course of action for technological regulation is the creation of global agreements for the sake of international cooperation, similar to the Nuclear Non-Proliferation Treaty. We felt this solution encompassed the greatest scope of ethical dilemmas currently plaguing the industry. It prevents any one nation from monopolizing the science or exploitation in light of their geopolitical ambitions. Furthermore, the transparency it provides not only enables cognizance on the protection of digital infrastructure, but also ensures that quantum computing can be integrated evenly and sustainably rather than centralizing in giant corporations. As we stand on the forefront of a quantum revolution, we hold the promise to define an era where quantum computing is synonymous with ethical integrity and steadfast flourishment. Thank you.
Just slide it up.
What questions do you have?
All right, Tyler, I'll start with you, and then we'll work our way across. Tyler, how did your group decide how to include David's information into your overall presentation?
Can you repeat that, please?
Sure. How did your group decide how to include David's information in your overall presentation?
David's perspective on cryptography, the encryption and decryption of information, benefited my presentation as I went over the ethical viewpoints of encryption and decryption, which helped governments and citizens control their privacy of information.
All right. Ruben, reflecting on your colleagues' work, which one had the greatest impact on your understanding of the problem you guys identified?
So I believe that David's perspective, when he spoke about like cryptography, he spoke about how supremacy, when it comes to information regulation, is like the biggest factor towards like towards technological leadership, and as a result, it deepened my understanding of our overall issue, as I understood how it was necessary to ensure that all nations and corporations across the world would easily be able to leverage the features associated with quantum computing to produce viable solutions to a variety of problems.
All right. David, what's a way in which your team's resolution, or I guess it would be problem solution, makes you think differently about the research you conducted?
Well, a lot of my research in cryptography was the implications were described by some of my peers' perspectives, such as Mark's discussion of adaptive radiotherapy and personalized drug discovery. So our solution for our global agreements and international cooperation allows for those kinds of uses for quantum computing to not be exploited, and especially with the emphasis on transparency, nations with tech giants, which are currently holding all of the quantum infrastructure, aren't able to develop projects in secret, and overall just heighten that technological leadership, which might fracture the industry.
All right. And save the best for last. Mark, what's an example of an argument from one of your peers' IRRs you decided not to use, and why?
So an argument from Ruben's IRR we didn't use was pilot wave theory, because he talks about spintronics and like how quantum computing works in the industries. So it wasn't really necessary, since he elaborated more on that theory instead of pilot wave theory.